it should be able to help you, that Christmas review should be able to help you along with this. If you want extra review material after you've completed the Christmas review, or like next week or something like that, you feel like you still need more review material, that's fine. You can come talk to me. I just don't want to murder 3,000 trees and hand out a bunch of stuff to everybody, even though maybe not everybody's going to do all the review booklets. Is that okay? So if you want to, come talk to me, and then I'll print some off next week, or I'll print some off during exam week or something like that. I got no problem with that. We are not going to review the bonding unit test, because there's still a buttload of people who have not written the bonding unit test. Pardon? The marks are not up. No. I'll try and mark them tonight, and maybe I'll put the marks up. But I would like to either review it tomorrow in class or Monday in class. I mean, there's no real rush to review that exam. Sooner or later, we're going to review it. Yes, there's a big rush to review it. Okay, well, we'll try tomorrow. We'll see how it goes. But anyways, so there's this. You can go ahead and read through that, and that should be able to kind of like let you know. There's information the very bottom back side of this checklist. Your final exam consists of 2 written response questions. What?
There were 6.
So when I say 2, I mean a page and a page. And it's 1 A, B, C, and then like 2 A, B or something like that. So, I mean, what's something that would be really nice if I could test you like as written? What's something where you need to be able to show me physically, not physically, but like on paper? What? Titration's probably a pretty good one. You know what I mean? Like a titration, that's where you have a chart, and it's got like a table, and it's got how much volume did you use in trial number 1, and how much volume did you use in trial number 2, and you have to figure out which trial you're not going to use, or if you're going to use all of them. Do you know what I mean? And then you have to take the average volume, and you have to do some solution stoichiometry to figure out an unknown concentration. Is that, like, I don't know, would you agree that's probably a pretty good bet for a written response question? Some sort of stoichiometry, yeah, you can better believe you're going to have a written question on some sort of stoichiometry. Titration is a pretty good example of one of those. Now, that's a math-related question. What's a non-math related question I could ask you as a written response?
The same one we used.
Something about bonding?
Yep.
Right? Anything about bonding? What about Lewis structures? Could I ask you to make some Lewis structures? Yeah. Could I ask you, predict the shape of this molecule? I mean, keep in mind, right? Am I ever gonna test you on stereoscopic perspectives of chemicals? I'm never going to ask you to wedge going in and wedge going out, right? So, okay. But right there, math-related question, non-math-related question. I'm trying to test you on your concepts and your ability to perform skills. That's basically what I'm trying to do. So, okay, perfect. So that's where the 12 marks comes from, Idris, is because probably there's multiple components to each of those. Hopefully that makes sense. 33 multiple choice questions. They're approximately equally spread out throughout the 5 units that we did. So if you go 33 divided by 5, that's 6.5 questions each. Ish, right? Yeah. So there's, roughly 5 to 7 questions from every unit. We've done 5 units. Okay, no problem. And there's 5 numeric response questions. So maybe 1 from each unit. Blah, 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 blah. Good? Okay. If you have any questions, I'm not asking you to look through the whole thing right now, but if you have any questions, feel free to ask me. I'm here basically every day during exam week. Now, the first day of exams, that's when everybody's Math 10, Math 20, Math 30 exams are going to be, right? Next Wednesday. So if you've got Math 10 or 20, then you have an exam that afternoon. If you have Math 30, you have an exam that morning. Every teacher in the building basically is gone that afternoon. I'm just letting you know every teacher is gone because they're hauling us off to Hunting Hills and we're supposed to be collaborating with our Hunting Hills partners, okay? Because we care about students in Red Deer, so we're trying to get the best possible information, courses, we're trying to share ideas, and we're trying to be the best possible teachers we possibly can be across the entire district. So if they do something awesome at Hunting Hills, we want to know about it. If we do something awesome here, we want them to know about it. So nobody's going to be in the building basically Wednesday afternoon. Just letting you know right now. I've got supervision of an exam, so I have to supervise an English exam. It's good. They put me in an exam I know absolutely nothing about, so that's fantastic. I can't help anybody cheat. That's wicked. So if you've got an English 10 or 20 exam, I might be supervising you Thursday. So just letting you know, I'm not available Thursday, like afternoon. But then in the mornings both days, I'm fairly available. Friday, all day, fairly available. Monday, basically all day, fairly available. Tuesday afternoon, that's when your exam is. I want to be very clear. Tuesday at 10 o'clock in the morning, I will not be available for about an hour. I'm going to look at the Chemistry 30 diploma to learn what kind of questions are on the Chemistry 30 diploma to see if my teaching accurately reflects what's expected to be on the Chemistry 30 diploma. So I just want to make it very clear, Tuesday morning, the day of your exam, I will be mostly available that morning, except for a chunk of time between about 10 o'clock and 11 o'clock. Your exam's at 1, so just plan accordingly. If you come in freaking out at 10 o'clock in the morning, I will be walking out the door and I will be unavailable to help you for a little bit. Cool? Cool, awesome. So what I want to do is I want to do some gas laws review. Yeah, go ahead, Maya, thank you.
Are we going to do a GOH thing?
What? I would like to. Is that okay with you? Ah, nice. Isn't it awesome when our values align like that? Okay. You could look at your checklist for bonding. You would just have to see where the gases. You would just have to see where the gases section is in that checklist if you wanted to. But we're going to go over kind of the main ideas from the gas laws unit. Now, keep in mind, this gas laws unit took us from about the second week of February all the way up, September, second week of September, all the way up until about the second or third week in October. So this was, I don't want to freak you out, but approximately 3% of your life has elapsed since we last talked about gases, basically. So this was a while ago. In the grand scheme of things, this was a while ago. Okay? Do you remember P, V, T, and N? Do you know what they mean? Power, velocity, time, right? No. What's PVT? Pressure, volume, temperature. Sometimes T means time, right? But this isn't a physics class, this is a chemistry class. So T means temperature, right? And N, what's N? Number of molecules, moles, right? Number of moles. Are we, okay, do we want to write this down? Yeah, we should write this down.
I just wrote it. Like I just did the work. I didn't understand that voice. What was this like unit all about again?
It's all about how gases change under different circumstances, their physical properties, and if we can predict what will happen to a gas under these circumstances. So, what? It's related to stoic, but this was way before we had an idea of one chemical reacting with another chemical. This is way before that, okay? This, a lot of this isn't about reactions, right?
This is like the green sheet thing.
Yeah, there we go. Perfect. Okay, temperature and chemical amount.
Oh yeah, chemical amount is moles.
Moles, right? Moles.
I lost my green sheet.
Shahad.
I lost my green sheet.
Okay, does anybody need a green sheet?
I'll finally do it, John.
How bad?
Just for the review, John.
Man alive.
Hey, what's wrong with that?
What is that?
Hands up if you need a new green sheet, but this time they're not green, they're blue. I'm shaming you. I'm shaming you. I'm saying blue is bad. Green is
I mean, mine is
green. Anybody need a blue sheet? Yeah, hands way in the air.
hired gimme
Hands way in the air. Let's shame you. Oh yeah. Oh, you got a green one.
I
Nice.
have a green one.
Oh.
I just put your John. This is the revolution.
Nobody else. Nobody else. Okay. Shh. So, shh. How are P, V, T, and N related? Well, let's think about a box, and let's think about two different scenarios. So we've got a box. The first scenario is where the box the volume cannot change. Okay? The volume of this container cannot be changed. And then let's think about another scenario where we've got a box, but it's got a lid on it. It's got a lid on it, and this lid can be moved up and down. So it's got a lid on it, and the lid can be moved up and down. So can the volume change? Yes, absolutely, the volume can change here. Yeah, the volume of whatever gas, whatever thing is occupying the inside of it, right? So let's take a look at this. I'm going to put the same number of molecules in both of these containers. How many dots do you want to draw? 7. Okay. Perfect. Mine are not necessarily equally distributed, but that doesn't matter. So, let's say the volume of this box equals 1 liter. Let's say the volume of this box right now is 1 liter. So I'll say VI. In the first scenario, what things are fixed? What things cannot be changed, at least right now? Can we change the volume? No, volume can't be changed. But what else could we change about this scenario? Could we change the temperature in here? So let's change the temperature. Let's adjust the temperature of these gases So I'm going to put fire. Ooh, okay. What's going to happen to my gases?
Go faster.
They're going to move faster. Would you say by adding energy to these gases, if they gain kinetic energy, they move faster. And if they move faster, what happens to the pressure inside the container? It gets greater, right? It increases. Okay, for two reasons. Okay? For two reasons. And it all has to do with collisions with the wall. Talk to me. What happens when these molecules move faster? They bump into each other and the wall more frequently. Would you agree? More often, but with more force behind it as well, right? So both of those things increase the pressure. So the pressure will increase. So an increase in temperature will cause an increase in pressure. Now, that's not the only thing that I could do here. Instead of increasing the temperature, what else could I do? Could I add more molecules of gas? If I doubled the number of molecules of gas, what's going to happen to the pressure in here? It's going to increase. It's also going to double. Because what happens with every one molecule, it hits the side. But if you have two molecules now, it hits the side twice as often. So the pressure is getting doubled, right? So if I increase N, that causes an increase in P. And the converse is also true. Would you say if I took gas molecules out, the pressure would decrease? Okay, all right, perfect. Now, what we're going to do is we're going to take this lid and we're going to squish it down. Okay? And what happens as we decrease, I got to group them together. Group, and then I got to walk, allow, move. Perfect. So when I move the lid, when I force the lid down, what happens to all of these chemicals? They're getting compressed, right? Gases are compressible, so we can do this. That's no problem. What's going to happen to the pressure?
It's going to rise.
When I decrease the volume, that causes an increase in pressure. One thing that's really weird, though, when you decrease the volume, what also happens is you actually increase the temperature inside here as well. When you decrease the volume, when you cram all of these molecules into a really small space, you increase the temperature as well. We'll come to that a little bit later on, okay? Okay, all right. So is it also true that if I would have increased the volume, the pressure would have dropped? Is that okay? All right, okay, that's good, perfect. Now, let's go back to our original scenario. If I increase the temperature in here, keep in mind my lid can go up and down. So basically what I want is the pressure on the outside is going to equal the pressure on the inside. I want them to be equal to each other. Think of a balloon, right? A balloon if you put more molecules of gas inside a balloon, the pressure goes up, right? But because the pressure goes up, what happens to the balloon? It gets bigger. Do you agree? So in a balloon, the pressure on the outside and the pressure on the inside are always equal to each other, right? Okay, cool. It's the same thing here. Because the lid can move up and down, the pressure on the outside is always going to be equal to the pressure on the inside. I just wanted to show you that, okay? So what's going to happen if I increase the temperature? What's going to happen if I increase the temperature? It's going to, I think people are either ahead of me or they're doing two things at the same time. What's the increase in temperature going to do to the pressure? It's going to increase the pressure, but the pressure is always the same inside and out. So how could the pressure be maintained inside? If the volume gets bigger. Would you agree? So an increase in temperature actually causes an increase in the volume only because the pressure has to be equal to each other. The pressure has to stay constant. Are we kind of getting a sense of how pressure, volume, temperature, and the number of moles are related to each other? Like, are we loosely kind of getting these? Yeah, we're reforming these neurons. Perfect, awesome, thank you. Okay, so we're gonna do a little bit of math now. If you have a balloon at 98 kilopascals and it's filled, goodness gracious, with 2.4 liters of air, what would be the pressure if it changed to be a volume of 3 liters? Now, what I want to bring your attention to, is there a change in something happening? Is there a change in something? Did you start with a certain pressure and you're ending with a certain pressure or something like that?
Yes.
Yeah. So which equations are we going to be using? Boyle's-Charles law or the combined gas law, right? You're going to be using with something with 1 and 2 in it. The combined gas law is the one at the very top. Not very top, but the one at the top of... No. It's, do you see there's 3 equations with 1s and 2s in them?
Yes.
There's P1 V1 equals P2 V2. That's Boyle's law. There's V1 over T1. That's Charles' law. And if you combine them together, it's PV over T equals PV over T. Yeah, so there's 3 different relations there. Does anybody need me to throw a calculator at them? Okay, let me ask that in a different way. Does anybody want a calculator today? Luke, you got one? All right, good. Okay, so let's see if we can do P1, V1, P2, V2. Remember, it doesn't matter what units these are in as long as the pressures are in the same units and the volumes are in the same units as well. If you have a balloon at 98 kilopascals, does that sound like an initial pressure or a final pressure? Initial, so P1, right? 98 kilopascals. So far, how many significant digits are we limited to? 2. So in our final answer, we're going to have 2. Okay. It's filled with 2.4 liters of air. So what's that? Initial volume. And then P2, we don't know. Do you agree we're looking for P2?
Yep.
Question mark. And then V2 is 3 liters. Squiggly line. So let's write this equation. P1 V1 equals P2 V2. What am I looking for?
V2.
You want P2. How do I get P2 all by itself? Divide by V2. So P2, P1 V1 over V2. .98 kilopascals times 2.4 liters divided by 3.0 liters. What happens with all of my units?
Liter.
Yeah, liter, gone. What am I left with? Kilopascals. And this is where I'm relying on you. This is going to be like 79 or something. Oh, is it 78? 78.4. Okay, good. So 78. Good. 78 kilopascals. Any questions on that? Charles's law is harder. Charles's law is way more difficult, okay? Because it's got V1 over T1 equals V2 over T2, okay? if you want to, if this confuses you, if you're like, man, I don't know how to get T1, I don't know how to get T2, then immediately multiply by both T1 and T2. Do you remember that?
Yep.
So then you're going to get T2 V1 equals V2 T1, and then that way it's way easier to rearrange it. Way easier to rearrange it. So I just want to give you a heads up. Okay, let's mosey. Let's keep going. You need to be able to perform calculations based on the gas laws under STP and SATP conditions. Hey, the first thing I think of when I think STP and SATP, what? What is it? You have, temperature and pressure, right? But the first thing I think of is not what those conditions are. The first thing I think of, if you look really close to the top of the page, it says the volume at SATP, right? So it's got molar volumes here. It says VSTP is what? 22.4 liters per mole. What does that mean? 1 mole of an ideal gas under STP conditions will take up how much volume? 22.4 liters. If you had 2 moles of gas under STP conditions, how much? Double the volume, right? That's the first thing I always think of. STP, SATP, molar volumes. Molar volumes all the time. Calculate the volume. So what are we looking for? We're looking for volume measured in liters. Under what conditions? SATP, right? So if we want liters, do you want liters on top or bottom? So 24.8 liters per 1 mole. And how many moles of gas are there here? 3.65. Unfortunately, I'm not a good enough mathematician to be able to do this in my head. 90. 90.5. Good. Okay. 90.5 what? Liters. Yeah, 90.52, but I mean, how many significant digits? 3. Good. Awesome. Okay. Calculate the chemical amount. Good. Calculate the chemical amount in moles. If you have 45,000 milliliters of gas at 70 degrees Celsius. So loud. Oh my goodness.
All right.
That's okay. And a pressure of 110 kilopascals. Let's think about this. Do you see a change in pressure, temperature, volume? No, there's no change. And there's no P1, P2 or V1, V2. Is this under SATP or STP conditions? No, son of a gun. Our only final, our last ditch effort is the ideal gas constant. R equals 8.314 liter kilopascals per 1 mole Kelvin. Hey, what are you looking for? What do you want to find? You want to find chemical amount. Which one is chemical amount? It's moles, right? So we'll put that on the bottom. We're looking for moles. 1 mole Kelvin over 8.314 kilopascal liters. Shh. What do you want to cancel out? Not everything. Except for moles. Okay. Where do you want to put Kelvin?
We have to change it to Kelvin.
Yeah, we're not even given Kelvin. So what is the temperature in Kelvin? add 273, so 343 Kelvin. Do you remember that? Yeah, okay. Where do you want to put kilopascals? On top, 110 kilopascals. And where do you want to put liters? Yeah. You don't have to change milliliters to liters right now, because you're going to have an extra milli. So we'll just have millimoles left over. But probably you do want to change it. What's 45,000 milliliters? 45.000 liters over 1. Prove to me you can do this in your calculator.
Will they
You're gonna watch it.
Yeah. What?
on the exam, well, if we leave it as millimoles, at least is it still a valid answer or no?
Well, it'll tell you what unit we want it in.
Okay.
It'll tell you which unit I want it in. So if all the multiple choice answers have moles, then you need moles. If they're all millimoles, then you need millimoles. Yeah. Prove to yourself that you can do this. 1.74.
Yeah, maybe.
Okay, I want to be very clear. We just reviewed 70% of the unit. Okay? Yeah, we just reviewed 70% of the unit. Now, there's lots of crap that we didn't go over, right? Okay? What we wanted to do, Newton and I wanted to make sure that you had time to do something other than listen to my voice drone on and on all the time. Would you say I have a fairly monotone voice? Yeah, I would say historically I have a very monotone voice. So we want to get you to do something other than that. Okay? So what we're going to do is we're going to do a lockbox activity.
Yes.
Have you ever done this before? Yeah? Do you know what the goal of this is? To open the lockbox. How do you open the lockbox? Okay, maybe I should think out my questions a little bit more thoroughly next time. How do you open the lockbox? You unlock the locks. Okay, yes, I totally agree with you. You open the lockbox by unlocking the locks. But you have to solve problems related to... You don't, there's a treat inside for you. It better be money?